Hello everybody, good morning. Hope you all had a good weekend. Um, it's time to talk about volumes again. Let me just say that the homework is due tomorrow. As a reminder, it's on Gradescope. The assignment is on our class website, and you can submit it on Gradescope. 2 people have already submitted it. Thank you for that. The rest of you got until tomorrow night. At midnight. Please let me know if you have questions about it. I hope that, these are mostly review problems at this point, so I hope that everything works out all right, but I'd be happy to chat about it. Anybody have any questions about the homework before we get going? Nope. All right, great. Let's talk some more about volumes then. We started off talking about this last time. I will just refresh our memory. The idea is if you have a shape which is formed by spinning a certain function around the x-axis. So typical example would look like this. We have this function, and then I'm going to spin this around the x-axis, and it makes something that looks like that. This kind of a spinny shape, all right? And we can find the volume of such a shape if I want to go, say, from x equal a to the end is x equal b. The formula for this is integral a to b pi f of x squared dx. All right, this is where we ended up last time. I think I just told you the formula, and then we had to go. But the idea behind this, so you should remember this formula. But the idea behind this is that this right here represents pi r squared h, which is the volume of a cylinder, which is the shape that you get if you were to slice this up into a bunch of little bitty slices. Each one of them is a cylinder, or it's like, it looks like a coin or something. That is a cylinder, where the radius is like this, and the volume of such a thing is 2 pi r h, where the h is this way. Now, in this example, in this setup, the h, the thickness of each of these slices, will be kind of infinitely thin when you're doing the integrals. That becomes the dx part. And then the rest of it becomes pi r squared. The r is given by the height of the function. That's why this is pi times f of x squared. All right. So this formula you should remember, and it would be good if you remembered a little bit about where those things came from, because we're going to see later on today, we're going to do some fairly simple variations on this, where to remember how to do the variations, you will want to have in your mind just the fact that this, the reason why this says pi times f of x squared is because it comes from a pi r squared. All right. In this formula, the pi is a constant. You can always factor the pi outside of the formula if you want to. Let's try an example. How about a shape like this? If we start with the parabola here, y equals x squared, and I go over to 1, and I spin this around the x-axis. You get this kind of a bugle shape. Delightful snack food, the bugle. I don't know what they're made of. They have salt, though. All right. I would like to find the volume of this sort of a bugly shape. So find this volume. All right. Our formula is integral a to b pi f of x squared dx, right? And this one is meant to be pretty easy. I told you what the function is. The function is x squared, and so this I can say is integral, let's talk about the a and the b in a moment. It's x squared squared, right? The function itself is x squared, but because of the formula already had a squaring in it, so it's going to be x squared squared. The pi is there. What about the a and the b? Anyone want to tell me what are the a and the b? Actually, did I even tell you? The a and the b should be these two x values. I suppose I didn't tell you. The one on the left you can tell is 0. The one on the right, I intended for you to use 1. So I asked you to say it, but then I said it because I didn't actually tell you. All right, we're going to integrate 0 to 1. Okay, Excellent. So I guess we can just do the integral. Any suggestions? How are we going to handle x squared squared? What is that?
You just add the exponents.
So you get
X to the fourth.
Yeah, it's x to the 4. Although actually in this scenario you don't add the exponents, you should be multiplying the exponents. But you get 4 also. So it is 4, x to the 4, pi x to the 4. When you have a power inside another power, you multiply it. When you have like 2 different powers of x multiplied together, you would add the exponents. Anyway, it's like that. 2 times 2 is the same as 2 plus 2. Let's do the integral then. So I get pi times 1/5 x to the 5, right? And we're plugging in 0 and 1. This is the antiderivative. I plug in the 1. I get pi times 1/5 times 1 to the 5th. And then subtract, plug in the 0. Pi times 1/5 times 0 to the 5th. Pi over 5, right? That's the answer. Strange answer. Strange but true. That's the volume of that little shape there. Any questions about that? I hope I did it right. I don't know if you've been watching these videos on YouTube. I got a comment almost immediately on the first video because I messed up one of the U substitutions just from some random person on the internet. Who, thank you, random person on the internet. Please let me know if you think I mess them up. I do often add numbers together wrong or something. I left out a minus sign in one of the examples. All right, smash that like button. Okay, that was a simple example. Okay, let's we got some time today. We're going to do some slightly fancier examples as we go. How about I'm going to say you can do this for many, shall I say, ordinary mathematical shapes. Can be computed in this way. I mean volumes, shapes, many volumes of, I gotta get this right, grammatically correct. Many volumes of ordinary shapes can be computed like this. For example, let's try the volume of a sphere, all right? Now you may, I don't know if you remember, but there is a formula that you learned at some point for the volume of a sphere. But I want to do it sort of by hand without using that formula. Can we do it? In fact, this is where that formula comes from, doing integrals like this. At least that's one place you could get such a formula. Let's find the volume of a sphere of radius 2. 2. All right? Let's see if we can work this out. A sphere of radius 2. Okay. Anybody actually remember the formula, just so we can check our answer? Any formula masters out there?
4/3 pi r cubed.
Yeah, it's 4/3 pi r cubed. 4/3 pi r cubed. I don't care if you have such formulas memorized. So, but anyway, in this example, we expect to get 4/3. Come on now, 4/3 times pi times 8. In other words, 32 pi over 3. So if we do it right, that's what the answer should work out to be. Let's see if we can do this. You have to think of this sphere as the result of rotating some function around the x-axis, right? Because that's the only this formula here is only good for a shape which is produced by rotating something around the x-axis. So I'm going to say this sphere is a rotation of what is the function which gives you a sphere when you rotate it around the x-axis? What do you think?
Would it be a parabola?
I don't think so. If you rotate a parabola, I mean something like this part of a parabola, you get sort of something kind of sphere-like but sort of pointy. That's more like a football shape, a rugby ball shape, if you will. Any other idea? It's not a parabola. A sphere is you want to think is basically like a three-dimensional version of some common two-dimensional thing, right?
would just be a circle.
A circle, yeah. A sphere is what you get if you spin a circle around some axis. So this is a rotation of a circle. Now we don't want the unit circle, we want the circle with radius 2, right? Here I'm drawing only the top half of such a circle, but that's enough, right? Because if you spin just the top half of a circle, you will get that the sphere shape that we want. Okay, so this is a rotation of this circle of radius 2. Now we have to figure out a formula for that as a function, right? We want f of x. And anybody recall, how do you find f of x for the top half of a circle? Or maybe, anybody remember the formula just for the whole circle, perhaps? The graph of a circle of a certain radius?
It's something like r times x minus h squared plus y minus k. Is that what you're talking about? That's right.
Maybe something like that. That is maybe a fancier version. Here we want a circle around the origin, which makes the formula a lot simpler. It has some x squareds and y squareds and r's in it, maybe. Anybody remember what I'm talking about? How about this? I'm referring to this formula. X squared plus y squared equals r squared. This is the basic formula for a circle around the origin with a certain radius. All right? I think maybe what she said, if you insert other things in here, you can get a circle around a different point. And if you insert constant coefficients, you can get an ellipse with various wider parts and thinner parts, but I don't care about that. So this is what we want. In our case, of course, I want the radius to be 2, so this will be 2 squared will be 4 in our example. And we need to write this as a function. That is, we need to solve it for y. Solve for y. That would be y squared equals 4 minus x squared. Take the square root. Y is square root of 4 minus x squared. This is the function we're going to use. Now, because I took the square root there, this is only going to give me the top half of the function, but that's fine. That's actually all I want in this example, is the top half of the circle. All right, so this is our f of x. Everybody good so far? Any questions about this? I know this kind of requires you to remember some random knowledge about equations of circles and whatnot. But these are things, you know, on a test, I probably would expect you to know this formula for a circle, but other kinds of obscure geometric formulas I would not expect you to have memorized. On the homeworks, I would expect you to look it up if you had to know one of these. All right. Okay, let's do it then. I'm gonna do the formula is integral a to b pi f of x squared dx, right? It is, I'll talk about the a and the b in a moment. Pi f of x is this function, square root 4 minus x squared, squared dx. What do you think? How about those a's and the b's? That would be the x values that we want to go across when we rotate the shape. What do you think? The range of x values this way. Yeah, did someone say something? Sorry.
-2 and 2.
Yeah, minus 2 to 2, right? That's just because our circle is radius 2. The range of x values is going to be minus 2 to 2. Excellent. So I put them in there. All right. And let's see if we can do the integral. What's going to happen? You should try to simplify inside before doing the integral. What do you think about square root and then the square there? I think the square is just going to like kill the square root sign, right? They will cancel each other out. And so I get pi. Do you mind if I factor the pi out of the integral? What remains is just 4 minus x squared, right? The square root and the square cancel out. It's a good thing too, because if it were just the integral of the square root of that stuff, that's not an integral you can really do without some very fancy tricks, because the square root messes it up. You might want to do a u substitution, but it wouldn't work. Anyway, this is the integral we have to do. Now it's not a hard integral to do, right? I got pi outside, 4x minus 1/3 x cubed. And I'm going to plug minus 2 and 2. Right, the 4 became 4x, x squared became 1/3 x cubed. And then you plug those guys in. So it's going to be pi 4 times 2 minus 1/3 2 cubed minus pi 4 times minus 2 minus 1/3 minus 2 cubed. There you go. This I would just leave like this ordinarily, but would you believe me, if you tried to simplify this, you do indeed get 32 over 3 times pi. And that's what I said the answer should be before when we use the formula for the area of a sphere. All right. One thing I always wondered about in that formula for the area of a sphere, it ends up being 4/3 pi r cubed. Where does the third come from? You know, the area of a circle is pi r squared. The pi r cubed in the sphere formula doesn't surprise me, but the 4/3 is a little weird. The 4/3 basically comes because you are integrating something that's a x squared, and so when you take the antiderivative, you end up getting thirds, and the 4 comes from adding together a bunch of thirds, basically. All right. Any thoughts about that? So this example was a little harder because you had to think about what the shape was and then think of a formula for that shape and all that. All right. I got a couple more, and I have one for you guys to try also. All right, let's try another sort of common shape. Another geometric shape, if you will. A cone. This is a cone. Let's see if we can derive the general formula for a cone with radius r, and this is usually called the height, because usually, you know, you draw the cone as standing up. But let's say the cone has radius r and height h. This is another sort of ordinary mathematical geometric shape. Anybody happen to remember the volume of a cone? There's a formula for that too, which I don't care if you remember or not. But let's see if we can figure out that formula. Let's find the volume. And I will tell you, anybody actually remember this? No, I don't either. Yeah, that's right. Pi r squared times h over 3, he said. Can I write 1/3 pi r squared h? That's how I would typically write this. Yeah, actually, this is not something that I have memorized. You must be a master memorizer of formulas. I'm not all that great at memorizing formulas.
Good geometry guy.
Yeah, all right. Yeah, put this guy in your saved texts. You can ask him whenever you need a geometry formula. Let's see if we can find the volume using the integral. We would like to end up with that. So we're going to do the integral stuff. Integral. Sometimes people say integral. Do the integral. I spelled it wrong. Don't at me in the comments. Do the integral. And all throughout we're going to leave r and h as if they were constants. Right? We're going to treat the r and the h as constants, and hopefully the r and the h, they should remain in the answer. And if we do it right, this is the answer. This is the answer that we're going to get. So the r and the h, we treat them as constants, and they're just going to stay in the answer. We're never going to plug something in for r and h. All right. This one's a little tricky because, again, you have to think about what is the function that you're going to revolve around the x-axis in order to make this shape, right? This is sort of where we want this thing to sit, and that is the function. What would you say that function is? What kind of a function is it?
That one looks like just some sort of linear function.
Yes, I would say it's a line. In fact, it is, just because of the way I drew the picture, it is a line through the origin, and so it shouldn't be too hard to find the equation of such a line. So in this case, f of x is a line through the origin, and the equation of such a thing is just, you know, f of x equals, like the slope and intercept form would be mx plus b, but the b is 0 because it's a line through the origin. So all we really need to figure out is the slope of this. M is the slope. But we can say, what is the slope in terms of r and h? You know, the slope is the rise over the run, but I think we've already sort of said what those things are. What do you think?
Would it be R over H?
R over H, yeah, the rise over the run on the picture is already labeled. You know, this line here, it goes up R while it goes over H. So it is R over H times X. This is our function that we're going to spin around the x-axis. All right. And can we say, what are the two boundary values, like the a and the b? So the a and the b are, that would be this point and this point here. The one on the left is 0, right? How about the one on the right? Maybe, can you tell us, Julian? Talking about these,
left and right.
These 2 points here. This one is 0.
1.
It's not 1. These distances are labeled on here. I want the x value here. Is this far over? I think it's h, right? I said this distance here is h. So this point here along the x-axis will be at h. 0 and h. All right. This is a little weird to have something that looks like a variable in the boundary values of the integral, but remember, we're treating h as if it was a constant, so don't worry about it. Nothing weird really happens. All right, let's set it up. So I get integral from a to b. I'll just write the formula as is first. Pi f of x squared dx. Okay, when I plug in, I get 0 to h pi. F of x is r over hx squared, like that. Don't forget them parentheses, that it matters. All right. When I have stuff inside parentheses in that way, you're just going to square everything you see here. So this is going to be integral 0 to h pi r squared over h squared x squared dx. And now, in preparation for doing the antiderivative, I'm going to factor out the constants. As always, I pull the pi out, but we are also treating r and h as if they were constants, so they can come out of the integral too. So out of the integral, I get pi r squared over h squared. Integral 0 to h x squared dx. I kind of like how this is looking so far. Remember the true formula? I know one of you remembers it. 1/3 pi r squared h. So far, I do have a pi here, and I have a r squared, which I like, although I'm a little worried about that h squared, but it'll be fine. Do the antiderivative. Pi r squared over h squared is outside there, and then I have the integral of x squared, so that becomes 1/3 x cubed, plugging in 0 and h. All right, the x squared, take the integral, it becomes 1/3 x cubed. This is where the 1/3 in the formula is going to come from. It's from that step right there. All right, and now we got to plug in. We get pi r squared over h squared. Plugging in 0, I get 1/3 h cubed minus pi r squared over h squared. Plugging in, sorry, that first one was plugging in h. Now I'm going to plug in 0. 1/3 times 0 cubed. This is all 0 here because it's a multiplication by 0. And the other stuff there, that is the answer. We're going to simplify as much as you can, although there's not much you can do. It's just h squared in the denominator can cancel with h cubed over there, and you end up with just h left over. So it is pi r squared times 1/3 times h. And that's what we wanted to see, all right? So this is the formula for the volume of a cube. I think it's kind of cute that you can actually work this out and get that formula from somewhere rather than just, you know, somebody telling you the formula. This is where the formula comes from, or at least this is one way to see where the formula comes from. This formula, as has always been a little unsatisfying to me because of the 1/3. It seems strange to me, and the 1/3 there makes me feel like I should somehow be able to put together 3 cones, like geometrically, stack them up, 3 of them, and make them look like something else, maybe a cylinder, because if I took 3 of them, then I get pi r squared h, which is the volume of a cylinder. But if you think about it, like geometrically speaking, you can't really stack 3 cones and get anything, right? Because they're not conveniently shaped. So it is pleasing to me to see where this 1/3 comes from. It's not because you can stack up 3 cones or whatever, but it comes from the basically it comes from doing the integral of x squared. All right. Any thoughts about this? Questions about that one? All right, the volume of a cone. Okay, let's talk about some variations on this basic technique. One fairly simple variation is, what about rotations around the y-axis? Can I do a similar thing for shapes which are being rotated around the y-axis? The answer is yes. You basically just turn your head sideways or something. You do all the same stuff if it's rotated around the y-axis. You do it in terms of y, not x, right? So your integral that you set up, instead of some integral dx, is going to be some integral dy. And the function you write, instead of f of x, you have to solve it for x and get something like f of y. But all the details work out the same. We did something similar about area last time between curves going horizontally. Let's just try one simple example like this. How about a shape that you get if you start with a parabola but go around the y-axis this way? There's a name for this volume that you get. This is actually called a paraboloid. The three-dimensional version of a parabola is a paraboloid. And let's see if we can find the volume of a paraboloid which has the function y equals x squared going from 0 to 1, like that. Can we find the volume of this paraboloid? Y equals x squared, function going from 0 to 1. All right. This is not a very hard example. We just have to, because we are rotating around the y-axis, we need to solve everything in terms of y values, not x values. So we're going to do the integral a to b pi. This is my formula, right? I'm going to write it this way. F of y squared dy. You have to do everything in terms of y's, not x. Where this a and the b, they refer to y values. And the function you need to write in terms of y values also. In this case, we have y equals x squared. To get f of y, we need to solve for x, right? Ordinarily, we would like our function to be solved for y, but because we're doing it the other way around, we've got to solve for x. So x is, I'm going to use the square root of y, right? And this is the function that we're going to use. In some contexts, you need to worry about putting a plus or minus in there or something, but in this type of problem, forgetting the plus or minus gets you only 1/2 of it, but that's fine for our purposes because 1/2 spinning around is good enough. All right. Anyway, I think we can plug everything in now. So it's going to be, this formula here becomes integral. What are the a and the b? They are the y values on the two ends of this shape, which are 0 and 1, according to what I said on the picture. These are the y values. Sometimes you might have to figure out what those values are, but I told you, so no big deal. Pi square root of y squared dy. Right? This is the setup. And then this is an easy integral to do. The square root and the square will cancel out, so I get integral 0 to 1, pi times y dy. This becomes pi times 1/2 y squared, right? And I plug in the 1, I get pi over 2. I plug in the 0, I get 0. So this is pi over 2. Easy integral to do. Really, the point of talking about this integral was, or this example was the setup. Just how do you do it if it's rotated around the y-axis? The answer is not a big deal. You may have to rearrange your functions, solve for x instead of y, but otherwise it's all the same. Any questions about that one? All right, here is a variation which actually is more complicated. Not just a simple thing. So let's find the volume of something like, I have two lines here. This is y equals 2x. This is y equals x. So this one goes up to 2, right? And they both go over to 1. And I would like to take the area between them and then spin that around the x-axis. So the shape you get is kind of like a cone with a cone drilled out of it. Right? It's hard to visualize such a shape. I don't think I own anything which has this shape. Maybe like a cymbal, like a drum cymbal, has something like that shape. But this is like, it has thickness to it more so than a drum cymbal. Okay? Let's find the volume of that kind of shape. Now, this requires quite a, well, it seems like this is going to require quite a different method, although it turns out to be very similar in the end. But what is very different about this is all of these examples we've done so far are based on the fact that when you slice this figure up like this, each cross-section looks like a circle, and that's why you get pi r squared or pi f of x squared inside the integral. It's because each of the cross-sections look like a circle. But here, the cross-sections do not look like circles. Here, the slices look like, well, what can someone say? What do they look like? It's not like a filled-in circle because it's got wouldn't be all the way filled in. What does it look like?
Would it be like a washer?
A washer, yeah. You've done this before? This is what people call, they call them washers. There's actually a name for this shape. This is not, mathematicians don't like to call this a donut shape because the donut has like a roundness, thickness to it. This is called an annulus, is the fancy mathematical word for this kind of ringed shape. All right, but yeah, our book, and when you do this in calculus, this method that we're about to describe is called finding the volume using washers. All right. Sorry, the word annulus refers to a flat shape like this. Really what we are talking about is a sort of three-dimensional kind of washer type shape which has a little bit of thickness to it. Right? In order to find the volume using slices of this form, we need to know what the volume of each slice here. So the volume of each slice, in this case, you know, before when they were like circular with no washer-like hole in the middle, it was a cylinder and it was just pi r squared times h. Now, in this case, we have sort of, there are two different radii in play, right? There's like the radius all the way to the outside of this washer, and then there's another radius which goes across the inside of the washer. So these are, you know, our book calls these the outer radius, and this is the inner radius. And the volume of the entire thing would be as if we just took the volume of this as a cylinder, say the big thing with the middle filled in. Consider all of this with the middle filled in, and then you just subtract off the volume of the hole that's being taken out. All right. What that means is actually the volume of each slice. So instead of pi r squared h, which we used in the previous examples, you got to use pi times the outer radius squared h minus pi times the inner radius squared h. All right. And the way, I think this is not so hard to see why. I mean, this would represent the area of the whole thing without the hole drilled through the middle. And then I have to subtract out, this is like the volume of the hole itself. Did I say area? I meant volume. This is the volume of the entire sort of disc-like shape here. But then you got to subtract out this part because this is the part, the hole, which is being removed. All right. And then this is what goes inside the integral sign. So you integrate this. H becomes dx when you do the integral. All right. This is how we do an example like this. So let me just write this as a formula. It's going to look like integral a to b pi, and maybe I'll say r1 minus r0. Sorry, each one is squared, like that. I took this formula that I wrote before up here. This business, you can factor the pi out and the h out. And so really all it is these two radii subtracted and squared each time. So here r1 is the outer radius. And generally it's going to be in terms of x, right? Like this is where the f of x comes into play. And then r2 is, or r0 is the inner radius. Also, that typically will be a function in terms of x, although sometimes it's just a constant. All right. So let's see if we can do this in our example. Any questions about the setup here? It's a more complicated idea, but really the formula that results is not much more complicated. It's just you got to subtract the two radii instead of just having the one. So our example was this, where this is y equal x, this is y equal x squared, right? And I said I wanted to go from 0 to 1 here. This is the shape which is being revolved around the x-axis. So let's set it up. Integral. The a and the b are 0 and 1. Those are my favorite a's and b's to use. So it's going to be integral 0 to 1 pi. Okay. As usual, you can always factor the pi out of the integral. R1 squared minus R0 squared. That is the outer radius squared minus the inner radius squared. Each of those, in general, will be a function of x. Someone want to tell me what's the outer radius here? In terms of x? I just drew a typical...
The outer radius just be x squared?
X squared, yeah. Oh, this is wrong, though. So I meant 2x. I mean for these to be two different lines. The 2x, not x squared. Yeah, it would be that upper function, 2x. Right? I'm messing it all up today because I haven't been outside in a couple days. 2x. Remember, you got to square it there. And then minus the inner radius. The inner radius is given by the other function, which is x. like so. This is the setup, and now we just do the integral. You know, usually the setup is the hard part, and then you just got to do some fairly straightforward integral. Everybody clear on how I decided what the two radii are? I hope that made sense. The outer radius is all the way up to the top function. The inner radius is just up to the lower one. Let's see if we can do the integral then. So this should be straightforward. I'll pull the pi out. 2x squared minus x squared. When you square this out, I get 4x squared minus x squared, right? Make sure you square the 2 there. We can actually subtract. 3x squared dx, right? So I do the integral. 3x squared becomes x cubed, and I plug 0 and 1. Plug in the 1, I think I'm just going to get pi, right? Pi times 1 cubed minus pi times 0 cubed is pi. Bet you weren't expecting that. Pi from that weird shape. Its volume is pi. It's true. Any questions about that one? All right, I got one more slight variation, and then I have one I want you guys to try. One more slight variation is rotation around some other line. I mean, not the x-axis, not the y-axis, but just some other line. And we're only going to look at horizontal or vertical lines. But let's try, I got an example here. Let's revolve the area between the x-axis and the function y equals x squared. And this is going to look a little confusing. You gotta make sense of this in a moment. About the line y equals -1. All right. So you will want to sort of draw yourself a little diagram to understand all of this nonsense that I just wrote here. The area between the x-axis, y equals x squared, and x equals 1 and x equals 2. So maybe I'll put those two values first. This is going to be the a and the b in my integral. I want the area between the x-axis and y equals x squared. Well, x squared does like this, right? Goes up to 4 there, although I don't know if that's relevant. The area between the x-axis and y equals x squared. So that's this shape here. You gotta translate my. That's all of this, right? It's that shape right there. And your job is to revolve this about the line y equals -1. That's down here. This is the axis of rotation here. Y equals -1. And I want to spin that around this line. So what results is like another one of these down here. And this kind of empty space in the middle, right? You get something that looks like a Christmas tree holder or something. You turned it sideways. The base of a pillar, the ousel, if you will. Right? The volume of this candle holder or something, whatever that is. Pedestal. Okay, so we are, the main thing that's different about this one from all the previous examples is I am not revolving around the x-axis or the y-axis, but around a different line, all right? You still want to think about what shape do the cross-sections make? The slices here are washers, right? Just like the previous example, because there's like a hole drilled in the middle of this figure. So the slicers are washers, not discs. So we have to use this formula, pi r1 squared minus r1 squared, right? It is going to be dx, not dy, because I'm still you can still think of this as being sort of cut up into a bunch of slices going that way, right? The slicers are washers. And we got to decide what's the outer radius, what's the inner radius. Now, this is slightly tricky here because you need to measure the radius from this line right here. So we measure the radius from the line y equals -1, right? Because y equals -1 is where the figure is being spun around, and so the radius, the measurement of the radius has to start there. All right. So I'm gonna draw this picture again, just because it's getting a little crowded. It's like this, right? This is y equals x squared, and then here's my rotation axis down here. And so for the inner radius, I want this value, and for the outer radius, I want this value, right? These are the R1 and the R2. And you have to figure out a formula for each of those things, typically depending on x, although one or the other, you know, in certain examples, they might be constant, the same all the time. Actually, I think that one of these is constant. So here, the outer radius or the inner radius, anybody feel like one of them is always just going to be the same? I mean, as you move across in the x direction, one of those radii is not changing as you move across. What do you think?
I'm going to agree with that and say it's going to be the one on the left that's not going to change because that's going to be this, like, the radius of your inner hole.
Yeah, the radius of your inner hole. Yeah. What?
That sounded so
yeah.
weird out loud.
What is that radius going to be in this example?
That one's going to be 2 because you're one below the x-axis and one above the x-axis. You plug in 1 for x squared, and then you look at where that falls in relation to that other line, y equals -1.
Yeah, so I think maybe you got to mix up a little bit. Like, so this radius is always the same, right? That's what you said before. The radius of my inner hole. R0 is constant. It's always the same. I think actually it is just 1, isn't it? It's this distance. The distance from -1 up to the x-axis, right? You don't want to go all the way up to the curve. That's the other radius, right? That's the outer radius. So here, R0 is constant, and in fact, R0 is 1 all the time. Doesn't depend on x. All right. The other one does depend on x. It goes all the way from this line down here, all the way up to the function R1 in this case. Anyone think you can say, what is this in terms of x? You may be tempted to say it's just x squared because that's what the function is. But actually it's not quite just x squared. What's it going to be?
I think you're going to have to add an extra 1 because that line exists one below the x-axis.
Yes, I agree. You got to add 1. So this distance here is x squared because that's the distance up to till you get to the function, right? This is f of x. But then you got to add 1 because that's that down there. All right. So the outer radius here, this is a little tricky. You got to work this out. It is x squared plus 1. But once you have all these ingredients together, then you plug into the formula and you can do the integral without too much trouble. Any thoughts about that just before we finish it off? This is the setup. A little tricky. You got to sort of draw the picture and try and work out the various radii on the picture. All right, let's see if we can do the integral then. So it's going to be integral from a to b. Now in this example, it's 1 to 2. I didn't draw that here, but I did say at the beginning the x values are starting from 1 on the left up to 2 on the right. And then on the inside, I got pi. My formula is R1 squared. All right, this is going to require a little bit of re-simplifying on the inside. R1, remember, was that x squared plus 1. You got to square it. And then minus R0, the inner radius was 1. You got to square that, although that doesn't matter. All right. Simplify inside before doing the integral. You got to do the FOIL thing on that x squared plus 1, the whole thing squared. So I'll factor the pi out as usual. Do the FOIL. I get x to the 4 plus 2x squared plus 1. That's squaring out the x squared plus 1. And then I have that extra minus 1 was there. That was from the inner radius. The 1's there can cancel. Interval 1 to 2. And what remains is x to the 4 plus 2x squared. We did dx. And this works out to be a, polynomial. I can handle that. I get 1/5 x to the 5 plus 2/3 x cubed. And I go 1 to 2. And we plug the numbers. This is how we do it. 1/5, 2 to the 5 plus 2/3, 2 to the 3 minus pi times 1/5 times 1 to the 5 plus 2/3 times 1 to the 3. And that's my answer for the volume of that Christmas tree holder. All right. What do you think about that? Any questions about that one? That's a little tricky, but you got to sort of try and draw the picture for yourself and work out what those radii are. This is the method of washers to find the volumes of a weird shape. All right? All right, I want you guys to try one. This is similar. I would like... It's a similar kind of shape, although, slightly different. Let's try... Find this volume. I want a shape that, so from 1 to 3, it goes like this. This is a line, y equals x. I want this shape spinning around this axis. So it's a similar kind of, Christmas tree holder or something, but a little bigger, maybe, wider. All right, I'll give you a few minutes. See if you can think it through. You will have to. The hard part about this is figuring out what the inner radius is and what the outer radius is. How about this? Just so that, if we were doing this in a classroom, I would kind of walk around the room and check in and see how each of you is doing. Maybe I am going, just to simulate that, I'm going to put you all in solitary confinement breakout rooms, and I will visit each of you just to see how you're doing. I hope you don't mind me. I'm not trying to evaluate you, really. I just want to make sure everybody is understanding, and I want to help out if I can. All right, so I'm going to create a bunch of breakout rooms. Oh yeah, you're going to lose my picture as soon as I put you in the solitary. So make sure you copy down the picture or take a picture of the picture. Picture in picture. All right, I'm doing it. All right, sorry I didn't have time to get around to everybody. But it sounded like people were doing pretty well. I hope that you were. You need to, like, the hard part about the setup is you need to decide what is the inner radius and what's the outer radius. So in this example, I think it's not so hard to say the inner radius. That's this, this sort of blue line over here. It is 3 in this case. That's because the rotation axis is down here at -2. And then you need to go up. So this little distance here, if you were to break it down, you could say this distance here is 2. And then you go up 1 more, and so you get 3 for the inner radius. All right. How about the outer? Any question about that? It's 3. Okay, the outer radius. This is a little trickier. I saw several people said x plus 3, but that's not quite right. The outer radius is the distance from here up to x. Now, x is the function value. Of course, the height of the function is always measured from the x-axis. So this height is f of x, which is x in this example. To get the outer radius, we need, the outer radius is like the length of this long red line. What's it going to be? You need to add on, you know, that much. I hear something, but it's not any of you, I don't think. Somebody's mom? I don't know. It's not my mom.
It would be x plus 3.
It is not quite x plus 3. Sorry, that's distracting me.
X plus 2.
It's x plus 2, yeah. This distance here is x. This is a little tricky. This distance here is x because the function, you know, the function value is x, which is always measured from the x-axis. So this height is x, this is 2. And so the total distance here is x plus 2. Take that, Mom. I'm sure she got that. All right. My mom was a math major, so I know moms can do this. My mom can do this. All right. So this is the basic setup. Let's just finish setting up the integral. I don't know if we need to actually compute the whole thing, but the volume is what? The volume is the integral. So my x boundaries are going to be 1 to 3. That's because the picture, horizontally speaking, goes from 1 on the left over to 3 on the right. And then I have pi, and then I have the outer radius squared, it's x plus 2 squared, minus the inner radius squared, which is 3 squared, like that. All right. And then this is going to work out to be a polynomial once we work out all the details. Square that out on the inside, I get x squared plus 4x plus 4, that's the FOIL thing, minus 9 dx pi integral 1 to 3 x squared plus 4x minus 5, like that. Just simplifying as much as I can before we actually do the integral. Do the integral. 1/3 x cubed plus 4 over 2x squared minus 5x, and then you plug in the 1 and the 3. Can I just say, etc.? I don't think we need to go through all the stuff at the end. All right. The you know, the more the part to emphasize for my sake is the setting it up, because that's the tricky part. All right. After you set up, I think everybody is capable of doing that integral. Any questions about the setup here? This is the volumes using washers. All right. Great. Let's talk about what we're going to do next time. So that was kind of the end of that section in the book. There are actually 2 sections, though, about finding volumes using integrals. And there's another completely different method which we can use to find the volume of a shape using integrals. So the next section in the book, and I'll give you the 5-minute introduction version of this. The next section is going to be, so maybe I'll just say this was what we've just been doing is volumes using washers, right? Or in a simpler in the simpler examples, they're just disks, solid disks without the hole in the middle. Then you just use pi r squared instead of pi r1 squared minus r0 squared. This was volumes using washers. Next section is going to be volumes using a different strategy, and this is what they call cylindrical shells. And this is a more complicated type of shape that you're going to draw when you slice the volumes up. Although it's not actually harder to do this way, it's just the shape you use is a little stranger, but it boils down to being a formula which is no easier or harder to use than the other formula. Cylindrical shells. Here's an idea, an example. How about this volume? That mom's back.
I think it's John Holt. You want to just...
Oh, yeah? Is he?
Oh, my bad.
Okay. Sorry, John. Talk about your mom. I don't know if it's your mom. I'm sure she's a very nice lady. or whoever that was. The volume. Okay, so here's an example of a problem in which you would not want to use the washers method, or you could use the washers method to do this one. But I want to describe how we could do it differently. This is the volume of rotating this thing around the y-axis. You get sort of a parabola-shaped bowl or something, all right? It looks like a cylinder on the outside, but it has this parabola dug out of it on the inside. Okay, let's find this volume. Now, you could do slices. So I'll just say you could do washer slices. Like this, cut it this way. And what you get each time will have an inner radius and an outer radius. The inner radius given by the parabola, and the outer radius would be like 1 for each of those slices, right? You get each of these slices would give you one of these washer shapes. But I would like to describe to you a different way, so a different approach. This approach is geometrically more complicated, but like I said, the formula that you end up with is no easier or harder to use. It's just a little stranger to wrap your mind around exactly this. What's a little more complicated is like if this were a piece of cake or something, you would not be able to cut this using a knife in the way that I'm about to describe. You could cut washers using a knife out of a cake. You just make straight cuts, all right? The cuts, though, that I'm about to describe are very weird. They are what the book calls cylindrical shells. How I'm going to cut this is I'm sort of going to cut it this way. But you have to imagine the cuts are not made with a straight knife, but the cuts themselves are sort of rotated. So this cut, for instance, its shape looks like this. The cut itself is also sort of a rotational shaped cut. Does that make any sense? You wouldn't, like I said, you wouldn't be able to actually cut things like this with a knife. It's more like you're punching holes out with a hole puncher or something. And the cuts that you get, so each slice, although it's not really like a slice in a straight line, each slice looks like it still looks kind of like a washer, but it's like thick this time.
Professor, do we refer to this one as a pipe as opposed to a washer?
You could say it's a pipe. The book calls it a cylindrical shell. That's the terminology. That's the standard terminology. Yeah, they look like pipes though, or they look like thick washers. All right. Each slice looks like one of those, and so the integral that you do would be set up in this way. You choose these 2 points as your A and B. Now on my picture it looks like 0 and 1, but in general you choose just whatever points you need. And the setup is quite different because this time, let's just look at the picture here. This distance, kind of what plays the role of the radius here, is just x, like however far across this point is. That is what we typically would call x. And the height of the pipe, or the cylindrical shell, is given by the function f of x, right? And so this is quite different from the washer's method, in which the height was like the delta x. The height was super small. In this case, actually, it's the thickness which is super small. The thickness becomes the delta x. I spell thickness like that because I know that's how the kids spell it. The thickness here is like delta x this time because we are thinking of slicing this thing up into super thin cylindrical shells, or these sort of pipe-like shapes here. All right. Anyway, what we have to do is add up, as usual, the volume of all those little shells. And I know it's about time to go. Let me just tell you the formula, though. So the formula for such a shape, so the volume of this, now you could write the volume of this like the radius, the outer radius minus the inner radius thing, but actually that's not convenient for doing the integral in this way because the radius is like the x, which is changing over time. There is no specific inner radius, outer radius. So it's more convenient to express the volume in this way. And this is a strange geometric formula that no one has any business knowing off the top of their head, but it's this 2 pi r h times delta r, where this represents the circumference. This is how you can remember this. The circumference around the pipe. This is the height, and then this is the thickness. Right? And so in our in using the variables, you know, from our setup, it's just 2 pi x f of x times delta x, which becomes dx in the integral. So the volume, this is our formula, and I'll leave it at this. We'll do examples next time. The volume using cylindrical shells, the formula ends up being quite different, but not any harder, really. You just have to remember a different formula. It is, the volume is integral a to b 2 pi x f of x dx. All right? No squaring of anything. You get this weird x times f of x. All right? This is the volume using cylindrical shells. And I think we'll have to leave it at that. We will do a bunch of examples next time. All right? See you all then. I hope you have a good day. Check out the homework if you haven't done it yet. It's due tomorrow night.